Hello, everyone. I am Raja. Today, I will present my solution for the EEDI mining misconception in mathematics competition, which was the first place in the private leaderboard. To start with, I will give a brief introduction about myself. So I am an AI researcher with a PhD in computational mechanics from National University of Singapore. After that, I was working with Evonik as an NLP data scientist. So Evonik is a German company focusing on specialty chemicals. So I was working with text-based application over there. After that, I was briefly working with Answer.ai as an LLM R&D. So at the time, I was working with all kind of LLM applications, as well as I was in the team that developed Modern BERT, which got released recently. It's a much needed upgrade on encoder models. And over the years, I have been participating in quite a few Kaggle competitions, mainly on NLP, and experience of those competitions helped me to do well in this competition as well. So moving on, I'll describe the task and my solution summary. So in this competition, the task was to find misconception behind an incorrect answer to a diagnostic math MCQs. One of the example of the diagnostic MCQ can be found in the right-hand side. Specifically, we would be given a math question and 4 options. Interestingly, we would also be given the correct solution for it. And for each of the incorrect one, we have to predict what would be the best misconception from within a set of around 2,500 misconceptions. Yeah, so by doing EDA on the dataset itself, I kind of found there are multiple challenges for this one. For example, first one would be counterfactual reasoning. What I mean by this would be, yeah, LLM are great at solving MCQs on math. So if we ask them to pick the correct answer from the 4, it is quite strong at picking the correct one. But if we ask them to follow, okay, this is the incorrect answer picked by a student, what could be the misconception of the student? So this kind of counterfactual reasoning, LLM is still not quite good. They are good, but they're not great. The second one would be closely related misconception. So as I mentioned, we had to deal with around 2,500 misconception. And if we look into them, there would be quite a few which are very closely related and differing by just a few clauses conceptually or computationally. So we had to tackle the closeness of these misconceptions. And finally, the generalization. In the training set, we had approximately 1,600 misconceptions, which meant there are quite a few, more than 1,000 new misconceptions that could appear in the private test set. So we had to build a robust solution that could do well in the unseen examples as well. Yeah, so these would be the challenges for this competition. Now this diagram shows a summary of my pipeline. So as I mentioned, we would have to deal with a diagnostic MCQ and an incorrect answer. And we would also be provided with a set of misconceptions. My solution would start with a set of retrievers. The job of this retriever would be, okay, look into this question and incorrect answer and find the top candidates, which could be the actual misconception. So I would retrieve 32 to 64 of those. And then once I have access to this set of top misconception, it would go through a series of retrievers, each with more and more capability as we move on to next stage. Yeah, so once I have this misconception, then firstly, it would go through a 14 billion parameter model, which is a fine-tuned coin model. And it has to process all those candidate misconceptions. And as an output, this model would produce the shortlisted top 8 misconception candidates. Then for the next stage, it would go to an upgraded re-ranker model, which is a 32 billion parameter model. Now it don't have to process all of the misconception candidate. It would just look into top 8 given by the previous stage. and it would shortlist top 5 among them. And finally, I have the most capable model, which is a 72 billion fine-tuned coin model. It would look into top 5 and it would produce the final ranking. Interestingly, after the stage 1 of re-rankers, I could already achieve around 0.615 in the private leaderboard, which is which would also given me the first position. And my training and inference codes are already public, and you could follow the links over here. Yeah, before moving on to the models, I would like to describe the data part itself. Yeah, at the start of the competition, I felt synthetic data is going to be key, mainly because it's math problem where we can verify objectively whether the given misconception is indeed describes the incorrect answer properly or not. Yeah, so based on that intuition, I experimented quite a bit on high quality synthetic data. Yeah, so ideally we would like to produce same quality of the training example as we were given in the competition itself. So I thought there is a set of properties that these synthetic examples should adhere to. Firstly is accuracy. So yeah, for each synthetic example, the picked correct answer should be indeed the correct answer. And secondly, it should have good diagnostic power. So we cannot randomly generate this incorrect answer. It has to probe certain kind of misconception. Yeah, so yeah, after that, it must have high resolution. What do I mean by high resolution is, as I mentioned, the misconception can be closely related computationally and conceptually. So the LLM that generates this synthetic data needs to know that. So yeah, so that it can discern between all these closely related misconceptions. And finally, diversity, which is self-explanatory. We need to cover as many misconceptions as possible. It is quite critical for generalization. In order to achieve these properties, for accuracy, I used LLM as a judge curation, which is quite standard nowadays. For diagnostic power, I provide very relevant reference example from the training set such that LLM knows what is a good diagnostic example for these misconceptions. Then for resolution, I kind of used a method which I call grouped or clustered data generation. What I did is to look into the pool of misconception and find the similar ones based on co-occurrence metrics. So here is an example down the slide. So all this misconception kind of deals with quadratic equation. Yeah, so during generation of synthetic data, if I provide the LLM access to this closely related misconception, then it can do a better job at producing example which probes them quite accurately. Yeah, so to be more specific, here is the prompt that I used. As you can see, I have this misconception cluster, which would contain top 8 to 16 closely related misconceptions. Then there would be the section of reference example, which would describe what is a good diagnostic example for maybe a few of the misconception in this cluster. Then this is prompt engineering. I would ask the LLM to plan or look into the reference example, try to find why it is a good diagnostic example, and so on and so forth, and have few guidelines. So after doing experiments, I could arrive at a set of good synthetic data, which contains around 10,000 additional example on top of around 2K examples from the competition. Now moving on to the models, the first one would be the retrievers. So here the job is to find top candidates for each of the incorrect answer for an MCQ. This is quite standard. I followed the standard contrastive learning process here, and the focus over here was to maximize the recall. Yeah, I didn't want to lose out on the actual misconception at this stage. So even though the metric of the competition was MAP at 25, but here when During development of the retrievers, I mainly looked into recall at 32 and try to maximize as much as possible. And following this logic, I kind of selected a lot of candidates. To be specific, I selected up to 64 ones. So for the example where the retriever was quite confident, I truncated it to 32. And for the ones which are kind of, there are quite a few candidates which are close to the most confident candidate from the retrievers. For those ones, I picked up to 64. And for the training of this retriever, as I mentioned, I followed the standard contrastive learning. And all these retrievers are based on LLM. And I fine-tuned them with LoRa with rank 64 and batch size of 128. Here I fine-tuned 3 models. So first 2 would be E5 Mistral and BGE model. These 2 are already retrievers, but I fine-tuned them with the competition dataset, which gave quite a strong boost. If you use the inbuilt one without fine-tuning, then they would score around 0.2 in the public leaderboard. So fine-tuning gave quite a good boost. And interestingly, I also could fine-tune Coin 14B model as a retriever. Since this was not a retriever or encode, since this is not an embedding model by itself, I had to do pre-training using all the synthetic data. Then after pre-training, I did fine-tuning of this model, and it became my best retriever. And with this model, I could achieve 0.93 recall based on my train and validation split. At this stage, interestingly, I could notice setting temperature to 0.01 instead of 0.02, which is typically used, consistently did well, both in terms of recall and precision. And there are a few other factors that help to improve the performance. I already mentioned pre-training of 14B encoder, as well as avoiding multiple demonstration of the same misconception in a given batch also gave strong boost. So I also tried quite a few things here. In contrastive learning, batching is quite important. And I tried in a given batch, all the misconception would be from a given subject, such that I thought the retriever could do well discern between misconception from the same subject. But unfortunately, it didn't do well. Any kind of custom batching strategies I tried didn't help. And then moving on, one of the important factors of my pipeline would be reasoning capabilities. So since this is math domain, and typically in math, you could generate chain of thoughts that would help the performance quite significantly. So my intuition was to use an advanced LLM and try to distill their reasoning capabilities in my solution pipeline. But of course, we cannot use them directly. So I had to distill them. Specifically, I created a synthetic data set again. So I would prompt Claude 3.5 Sonnet model. I would give it the problem statement, correct and incorrect answers, and ground truth misconception, and as well as several closely related ones. Then I would ask it to produce, okay, so what is the likely thought process of the student behind selecting this incorrect answer? Then it would give me around 4 to 5 sentence description of the likely thought process. Then once I obtain this data set, I could fine tune Cohen models such that they can predict the reasoning of incorrect answer during inference. And those reasoning would be provided to the re-rankers such that it helps them at ranking. So moving on, I had 2 pointwise re-ranker. By pointwise, I mean these kind of models would see one misconception at a time in the context window. Here is a prompt for this model. As you can see, there are several factors. One would be few short examples. Then there is the question and description. Then, as I mentioned, it could be enhanced with reasoning. So specifically here is the thought process. Then, as I mentioned, it only sees one misconception, which is over here. Then after forming this problem, I would ask, okay, So does this misconception lead to the incorrect answer? And based on the yes/no logic, I could determine the relevance of this misconception to the incorrect answer. Yeah, so I had two of this kind of pointwise re-ranker. One is 14 billion parameter model and one is 32. And 14 billion parameter model does all the heavy lifting because it has to process all the 64 up to 64 candidates. And I found prefix caching from VLLM was quite helpful to improve the efficiency of inference. And for this kind of re-rankers, I did quite a few experiments, and I found 4 factors that help to improve the performance. First one is context enhancement with few short examples. As all of us noticed, the description of the misconception are quite short. And if we can provide few reference examples during training and inference, it helps significantly for the model to learn what this misconception is about. Then the distillation. So distillation here means I first fine-tune a 72 billion parameter model and predict their score on the synthetic data. Then I combine them with the competition data set and synthetic data set and retrain the model. This is quite standard technique, and yes, and it helps significantly here. The negative ratio would be for each of the ground truth misconception, how many negative misconception I select during training. As I noticed, if you increase this number, the model learns better, and it generalizes better as well. Eventually, I selected 24 negative misconception for each of the positive ones. And finally, the chain of thought also helped significantly to generalize. And here is the ablation studies. As you can see, the private leaderboard score for my baseline without any of these techniques would be around 0.5 in the leaderboard. Then with the few short examples, it improved to 0.53. With distillation, it improved to 0.57. Then with negative ratio and adding more example, it pushed to almost close to 0.6. Then with a chain of thought, it pushed to 0.615. And lastly, I had this listwise re-ranker, which is the most capable model for my pipeline. It's a fine-tuned 72 billion parameter model, which is context enhanced, meaning it has access to a lot of reference example for the misconception it has to rank. And again, reasoning enhanced. Particularly here, I use 3 thought processes predicted by 3 reasoners. One is 7 billion, one is 32, and one is 14 billion. Yeah, and it sees 5 misconceptions at a time, and it has to rank them accordingly. Yeah, so that is all about my models. Now, a few interesting findings. Yeah, first one is kind of
just a quick time check. If you could start wrapping up.
Yeah, sure. This is my last slide.
Okay, great. Great,
Sorry
thank you.
about that. Yeah, so interesting finding is, yeah, synthetic data is useful, but yeah, it needed quite a bit of study and experimentation to get it right. The top embedding models from the MTV leaderboard didn't perform quite well without fine-tuning. So I thought it means the generalized embedding models is not doing so well. Then finally, the reasoning and context enhancement was very effective. Yeah, that's all. Sorry about the time.